to use this opportunity to thank Umlta for giving me this opportunity to discuss, to share knowledge on malaria diagnosis. Once again, my name is Twaha Kaga. I am currently the district lab focal person for Kasanda. I welcome all members who are here, and I call you to discuss as a team. We are going to discuss the laboratory diagnosis of malaria. As an introduction, malaria is a parasitic infection that is caused by Plasmodium. Currently, in Uganda, there are 5 known species, that is Plasmodium falciparum, Plasmodium malariae, Plasmodium vivax, or Plasmodium vivax.
Recording in progress.
Plasmodium ovale, and Plasmodium knowlesi. But if we do the lab diagnosis very well, that is a very important step in providing quality health care, because most of the cases that we receive in our facilities in Uganda and some other African countries are due to malaria. Today's session is going to cover the 2 common lab methods for the diagnosis of malaria in Uganda. That is microscopy and using of rapid diagnostic tests. We shall also look at the samples. We shall go through the samples we need in the diagnosis of malaria. Then we shall go through a simple step-by-step procedure for diagnosing malaria used by microscopy. Then we shall describe the features of the different Plasmodium species, because you cannot examine malaria under a microscope unless you have some knowledge on the features that distinguish one feature from one species from the other. Then lastly, we shall see how we report blood films for malaria. Okay, let us start with the common methods. The 2 common methods for the diagnosis of malaria are microscopy, which is the gold standard, and also malaria rapid diagnostic tests. However, there are other tests like molecular diagnosis, serology, indirect fluorescent antibody assays, and the quantitative buffer code. But for today, we are going to dwell mainly on microscopy and the RDTs. Microscopy is the gold standard in the diagnosis of malaria. It involves drying a blood smear, then staining it well, and examining it under a microscope. But it needs a lab personnel or any other person who is trained, and that person should be supervised sufficiently. Also, the equipment, the microscope, and the stains used need to be quality controlled to achieve microscopy. Then another method is the rapid diagnostic tests, also commonly known as the RDTs. This is an example of an RDT, a cassette, but these RDTs are used as an alternative to microscopy in places where microscopy cannot be achieved due to one factor or the other. But these RDTs employ the principle of immunochromatographic antigen detection, where dye-labeled antibodies bind. They are embedded in this cassette on a cellulose strip. They bind to antigens, malaria antigens, if they are present in a sample that is put into the cassette. They bind to that to the sample. After putting their buffer, then the resultant complex migrates along a cellulose strip inside here, and they give a test line. For this one, in this case, there are 2 lines. We shall see that there are RDTs that give 2 test lines, O1 Then there is also a control area where a control line is for integrity of the strip and the testing procedure. Now, we need to discuss a little more on how to perform malaria RDTs. We shall not go through the SOPs one step by step, but we need to a few points that need emphasis. The first point is reading and following the product instruction and the lab SOPs carefully. The points to consider here are the sample volume, how much volume is required for that specific RDT, the buffer, we need 1 buffer per test kit. We should not cross buffers from one test kit and use it to RDTs for another test kit. Then the timing of the test is also very much relevant. Then we need to make sure that the materials we need to conduct the test are there. For example, disposable gloves, swabs, and what have you. Then we should explain the procedure to the patient. Then we should check the expiry date of the RDT before we conduct the test. Also, it is advisable after checking the expiry date, we also check the color of the desiccant. This desiccant should be colorless or white. If the desiccant color has changed to pink, we should not use this RDT because chances are high that it has been spoiled by humidity. However much the expiry date might be still okay, but if the desiccant shows signs of contamination, we are not advised to use such RDTs. Then we are also advised to stick to biosafety standards, putting on gloves, disposal of waste, then disinfection, all those ones. Then we are also advised to use the RDT immediately after opening. Should not keep the RDT for long before applying the sample and the buffer. Then labeling is also a very important point we should emphasize while doing an RDT. Now, the samples we need. The samples needed for diagnosis of malaria are either capillary blood that is collected by the famous finger prick method, or we can prick other sites like the heel or the big toe. Also, we might need venous blood that is collected by vein puncture, where we puncture a vein. But the preferred anticoagulant for use is EDTA, that is in a purple top container. Then I'm going to take us through diagnosis of malaria by microscopy. We are going to go through a brief step-by-step procedure of diagnosis in malaria by microscopy. We are going to start with smear preparation. Smear preparation, each lab, we should make sure that we have a procedure for smear preparation. Also, we should follow these steps. All these guides that are in this presentation are for things we normally forget, or things we should emphasize. One is labeling. We should label the smear with the patient identifier. In this picture here, we have 5 smears. The 4 are labeled well with patient identifier, but 1 is not labeled. Then we should also emphasize appropriate staining. When we are to examine malaria slides by microscopy, we should emphasize appropriate staining. Then the positioning of the smear. In the picture here, there are smears made the same slide. Both the thick film, this round one, that appears thicker is the thick film, but there's also a thin film in front on all of these smears here. This is a technique where the smears were made on the same slide. There are also other techniques where the thick film is made on a different slide from the thin film. So the positioning is that the thick film should be in the center of a slide. If they are put on the same slide, it should be near the frosted end, then the thin film should be in front of it, just as these pictures are showing. Then we should also put emphasis on the quality of the slide and the spreader. When we are making smears, it is advisable that the slide is grease-free, as we are going to see in the next slides. It should be grease-free. Then the spreader should not be chipped. Then the slide should not have cracks. Then the competence of the person making the smears. This person should have the knowledge and should be competency assessed. Then again, when we are making smears, we should also consider the sample volume, how much volume is required for a thick film and how much volume is required for a thin film. Like this slide that I'm highlighting, the volume of the sample was too little, that the smears did not come out well. Then the first one on top here, the volumes were okay, that the thick film appeared well, and the thin film also appeared well. Only that for this first one, the thick film is too near the edge of the slide. You might even fail to get where to label on this slide. But this slide here, they put there much volume of blood that the person who made this smear could not even make the thin film. The tail was not seen. The tail is this somehow pointed end of the thin film. Then this slide here, this smear was made on a greasy slide that the smear ends up with having patches. The thin film has patches, even the thick film has patches. This same thing happens when you have kept your smear where there are pests. The cockroaches and the ants like feeding on blood, so that the smear dries with patches. Then this last one in the light lower corner was made with a chipped spreader. That's the thin film appeared feathery. So, and when I bring it back to this thick film here, the thick film was not evenly dried. That's why blood tended to move to one side. So when we're making smears, we should consider those items of sample volume, then the quality of the slide and the spreader, then the drying, the evenness of drying. Now, after making the smear, we go to staining. Smears for malaria microscopy are stained by a type of stains called Romanowski stains. The common Romanowski stains are Gemsa, Wrights, Jenner, Leishman, and Fields. These Romanowski stains have two components: the methylene blue component that stains the acidic part of the parasite and the cells inside the cytoplasm of the parasite. There are acids that methylene blue stains. Then the eosin stains the acidic part of the parasite. Inside the nucleus of the parasite, called the chromatin dot, there are basic components that have affinity for eosin. That's why the chromatin dot appears red, because it has been stained by eosin. We are going to go through, I'm not going through, for this presentation, I put here the staining procedure for Gemsa stain, one of the common stains we have. This one, since the presentation will be shared, we can go through it. But what we should consider when we are using Gemsa stain is the dilutions. How do we dilute the stock solution? Because for Gemsa, every day when we are starting the activity, we need to prepare a stock solution. The staining procedures for Gemsa are two. You use either of the two. There's what they call the rapid method that stains for a shorter period, that is 10 minutes, and the slow method where we stain for 30 minutes. It is a slow method, but it is somehow conservative. We use less volumes, but for the rapid method, you might end up utilizing a lot of what? Of stain. But this table here shows us how much of the stock solution we add to the diluent to form the final volume that we require for the staining. And I want to tell you at this moment that the diluent we use here is buffered water when we are making Umlta stain. Now, most of our labs in Uganda, our staining technique is field stain. Here is a procedure for staining using field stain. When we are using field stain, there is a different procedure for staining a thick film and a different procedure for staining a thin film. When we are staining a thick smear, we make sure that we dip the dried blood film in field stain A for an amount of time that depends on the thickness of that smear. Otherwise, let the smear be in field stain A until when it is visibly blue, because you might put it there for a short period of time and the smear color does not change. You end up removing it when it is brown, at times green. So we put it in field stain A until when it is visibly blue. Then we rinse it gently in clean water. Remember to change the water when it is so much colored. This water should not be so much colored because it is used for rinsing. Again, the time of dipping the film in field stain B depends on the thickness of the smear. Then rinsing and drying. After staining, the drying should be upright. If the smears are on the same slide, and you are drying it upright, let the thin film face, let the tail side of the thin film face upwards. Field staining technique for thin film is the reverse of the staining technique for a thick film. In other words, after fixing with methanol, fixing the thin film with methanol and allowing it to dry, we start staining with the field stain B. Now let us go to examination. When we are examining under microscope, we start with the times 10 objective to see the distribution of the cells. Then we shall go to the times 100, also called the oil immersion objective for the examination. This picture here on the right is the longitude. It is called the longitudinal method of examining. If you start your smear from this point here, please go up in that line, then come to a next field like this, like that. This is either this is the longitudinal method. You can do it north-south or east-west, but this is the advised, this is the best method, if I may say. Or it's the method I can recommend while examining blood films. Then, if we are examining for a thick film, we first look for sexual stages of malaria. If you see the sexual stage first, it's okay, but look for the stage of the parasite. These stages, we shall see them in the coming slides. Where we see the first sexual stage, we start counting the malaria parasites and the WBCs. We shall see that we count up to at least 200 WBCs. This will help us in reporting, as we shall see. That we shall also see that when we reach the last field, we count both the parasites and the WBCs. In the field where we have found our 200 white blood cell, then if we don't see any parasite, it is advisable that we examine at least 100 high power fields. We examine at least 100 fields if you have not seen a parasite. Then for a thin film, we are looking for malaria parasites, the different stages. But for a thin film, the red blood cells are not hemolyzed. Therefore, we look for parasites inside blood cells, except for one species where the gametocyte stage ruptures the cells. So we look for the parasites inside the cells, also the nature of the infected red blood cells. Now, we are going to the interpretation of results. How do we interpret what we see? This section is going to give us knowledge on how the malaria parasites look like under a microscope. This is a pictorial representation of how a malaria parasite looks like. This section inside here is the parasite. This is a picture of a parasite inside a red blood cells. This bigger circle is that of a pictorial of a red blood cell. Then the circle inside, the one I will say in the middle is the parasite. Then the small circle inside, that is white. This one is a vacuum. When you are looking for malaria parasites, you first look for red, I will say red dots. If you see some red dot, please check around the red dot. There is a crescent blue shape surrounding that red dot. Then that is the malaria parasite. In a thin film, it will be inside a red blood cell. If it is a thick film, you will look for a red dot with a crescent blue surrounding. This red dot in malaria microscope, we call it a chromatin dot. Then the surrounding eccentric feature that is normally blue is what we call the cytoplasm of the malaria parasite. Then between the cytoplasm and the red chromatin dot, there is an unstained area, what we call the vacuole. The vacuole. That is the basic structure of a malaria parasite. Then inside the parasite cytoplasm, there is some golden yellow or golden brown color. That color is for pigment, malaria pigment that is produced by digestion of hemoglobin by this blood cell. Then for the infected red blood cell, which we also call the host red blood cell, we look for its size in comparison to the surrounding red blood cells, or we also look for the cytoplasm of the red blood cell if there are changes. These changes in most cases are like some particles, dust-like particles, and those particles are called stipplings. Now, these are the different developmental stages of malaria parasites that are in blood. The first stage is called a trophozoite stage. The trophozoite is basically the ring form. It can look like this or like this in a thin film inside a red blood cell. This is a picture of a normal red blood cell. Then these two are red blood cells that contain trophozoites of malaria parasites. Then this on the right side here, these are trophozoite stages, how they appear in a thick film. I want to remind you that in a thick film, the red blood cells have been lysed and the malaria parasites are free. They look like that. They are these ones, the typical ones where there is a red dot and an eccentric cytoplasm. There are those ones with amoebic cytoplasms like this one and this one. Then there are those ones where the red dot is in the middle, then there are the cytoplasm on the other end. There's these ones that look like tears. There are various forms, as we are going to see in these slides. Then there's another stage called a schizoid. A schizoid in an uninfected red blood cell, there are numerous red dots inside a cell, numerous red dots. Also, they are pigments. These golden yellow structures are pigments. Then for a thick film, the red blood cells are hemolyzed, but at these later stages, the red blood cell that has been hemolyzed, it is difficult to finish it up. There is a ghost structure that stays there called the ghost cell, but these structures inside here with red dots and the blue cytoplasm are called merozoites. These structures are called merozoites. And these merozoites are the other stage I wanted to show, but this stage we don't report it. It's not common because merozoites are from inside schizons, but these merozoites look like this. Then lastly, the last developmental stage found in blood are the gametocytes. One species of malaria called the Plasmodium falciparum has banana-shaped gametocytes, which look like this, but they also have the golden yellow malaria pigments, also this ring of leftover of the red blood cells. Since they are banana-shaped, the red blood cell tend to rupture. Other species have gametocytes that have a big chromatin and a blue cytoplasm. This is also another gametocyte stage, probably of Plasmodium ovale, as we shall see. Then this is now not a picture. This one is not a picture. It is a schizont from a blood slide. This is not a pictorial representation. This is a schizont, how it looks like in a blood smear, as we shall see. Now we are going to see the distinguishing characteristics of the various species. We are starting with the Plasmodium falciparum. The first distinguishing feature of P. falciparum is the red blood cells. The infected red blood cell is not enlarged. It is the same size as the normal red blood cell. Another feature is the trophozoite stages of Plasmodium falciparum. The rings are very delicate, as you can see these ones. This is a pictorial representation of a thick film of P. falciparum. The rings are very delicate. Then issues of multiple infection, where you find there is a red cell that has two or more parasites inside. That is multiple infection. Then the issue of double chromatin dot, like this parasite here. The parasite with two chromatin dot is a feature of P. falciparum. Then the marginal forms of the parasite that is on the surface of red blood cells, what we call acoliforms. It is common, but it is better seen in a thin film, but it is a common feature of P. falciparum. Then the schizons and gametocytes are rare, but the schizons of P. falciparum, the cell size is not altered, and they have numerous merozoites inside them. P. falciparum produces the largest number of merozoites, up to 32 or 34. The cell size remains the same, but the merozoites are very many. In a thick film, since the red cell is hemolyzed, you will just see a cluster of many merozoites. Then the gametocyte has a crescent shape. Then when the parasite is developing, the infected red blood cell develops stripolings called Mora's dots or Mora's clefts, like in this picture here. Then there's also a picture here of P. falciparum in a thin film that can show that the red blood cell size is not altered, but there is a parasite inside the cell. Also, the Mora's dots are easily seen in that picture. Then also, this one is a multiple infection. There are two parasites in this cell, but also if you can look at the cell size, it's not infected. Again, P. falciparum is numerous. Like in this only field, there are 3 cells nearing one another, but all of them have parasites. Then the seasons in a thin film looks like this. The cell size is not changed, but there are numerous merozoites inside that cell. Then this is the gametocyte of P. falciparum in a thick film. You cannot, the edges are not so much visible, but the malaria pigment in the middle here is visible. Then when we come to P. malariae, the distinguishing feature is the compact cytoplasm. The compact cytoplasm, it has a compact cytoplasm and a larger chromatin dot. The chromatin dot for P. malariae is larger compared with that of P. falciparum. It also has this, the band forms in a thin film. P. malariae, the band forms are common, especially when the trophozoites start developing like this one. This is the band form. That is a parasite that is appears to be across a red blood cell. Then there is also a feature called the basket, the basket form. Oh, it's not there. There's also the basket form where the cytoplasm is surrounding the chromatin dot, that the parasite looks as if it is a shopping basket, like this one here. They also refer to it as bird's eye. It looks like the eye of a bird, also has a shopping basket with that handle. Then for the seasons, they look, there's what they call the daisy head appearance. They are so much as if they are organized. The pigment is in the middle, but the merozoites are organized around that pigment. That is a feature of P. malariae seasons. Also, the red blood cells that are not enlarged, but the distinguishing feature here from P. falciparum, where the red cells are also not enlarged, is that the merozoites are fewer. This one, the merozoites are fewer, like 8 in the season. Also, there's a lot of pigment right from the trophozoite stage to the seasons and up to the gametocyte stage. P. malariae, the infected are not enlarged, but there is a lot of pigment, like you see in these fields here. There's a lot of pigment. Sorry about that. Yes, now next we are going to look at Plasmodium ovale. Plasmodium ovale, the distinguishing feature is the fact that the infected red blood cell is made ovoid with sometimes with fimbriated ends. Like for this one, and this one, the ends are fimbriated. Also, the cells made ovoid. Again, in there's what they call sturdy cytoplasm. Cytoplasm is big and it is there, colored. Also, the chromatin dot is big and visible. Another feature of P. ovale is the stipplings in P. ovale are visible and coarse. They are called James's dots. They are visible and coarse. The red blood cells are somehow enlarged, but they look elongated or ovoid. Then the season of P. ovale is visible by the ghost nature of the James's dots that stay there. Even if in a thick film, they will stay there. Also, the fact, if you compared with the PVVAX, we are going to see that also enlarges cells, but the merozoites are much. Even the gametocyte of P ovale is differentiated by the ovo-like nature of the infected red blood cell and the coarse James's dots. This is a P ovalate trophozoite in a thin film. Then again, this is a chisel of P ovale. You can appreciate the oval shape of the infected red blood cell and the James's dots that are coarse and visible. Then for PVVAX, the distinguishing feature of PVVAX, one is the enlarged infected red blood cell. The red blood cell is so much enlarged, and there are numerous stipplings called Schaffner's dots. They are numerous, and also the amoeboid nature of the cytoplasm. In trophozoites of PVVAX, the cytoplasm is amoeboid in shape. Then for the schizons, the merozoites are numerous, up to 28, up to 30. They are numerous. Even in a thick film, I told you, you will realize they are bigger. That's what differentiates from that of P. falciparum. There is a heap, I would say a heap of merozoites. Also, the ghost shape left by the Schaffner's dots after the cell was hemolyzed. Also, the amoeboid nature of the cytoplasm. Those are the distinguishing features of PVVAX. Now, if you understand those distinguishing features, you can now make a good report of malaria using a microscope. But before we reach the report of malaria using a microscope, let us first see how we report malaria RDTs. Malaria RDTs, we report one of 4 results. Sorry, one of 3 results. The first result is the negative result. This negative result is when there is only one line in the control window. The control window is that they normally label it with letter C, as you may see in this case. This case of the RDT here tests for both Plasmodium and non-Plasmodium species, or the protein that is released by Plasmodium alone and the protein that is released by Plasmodium and other species. So when there is only one line in the window labeled C and there is no line in the window labeled T, we report that RDT as negative. Then the positive result. The positive result is when there is a line in the window labeled C, which we have called the control window, and 1 or 2 lines in the window labeled T. That is the test window. Even if the line is faint, we don't report faint or weakly positive. No, we report it as positive. Like this first one here, there is one line in the window labeled T, and there is also a line in the control window. This is positive. Then the next one, there is a faint line in the window labeled T. This one is also positive. Then there is one line again in the window labeled T, but in a different position from this one. So you have seen up, this is also positive. Then there is another one that has 2 lines. These are the common, these are the RDTs that the ministry is recommending as Ministry of Health of Uganda is recommending for use now because of mutations and what have you in the protein. So there are these ones that detect all the proteins produced in the early stages and in the late stages. So all these ones are positive. The bottom line is, for a positive result, there should be a line in the control window labeled C and in the test window. Then if there is no line in the control window, the window labeled C, there is no line like in these pictures here. Even if there is a line in T, whether it is there or not, that one is an invalid result. We don't report an invalid result but we are advised to repeat this test with a fresh sample at RDT. Now, we are going to see how we report the microscopy results. Microscopy results, we are going to go through 5 methods. The first one is parasites per 200 WBCs, then parasites per 500 WBCs. Then we shall see how we calculate parasite density, then the method of using plus sign, and the method of reporting parasites per field. Now, before you report, except for the parasites per field and the plus sign, but for these first 3, before you report, you first count. You count, actually even plus sign you count, all of them you count, but for the first 3 you count both the malaria parasites and the white blood cells. This example here, we have a picture of 6 fields which have both the representation of white blood cells as black dots and malaria parasites as blue rings with red dots. In the first field, there are 4 parasites and 7 white blood cells. Let us assume we are examining under the microscope. When we got the second, there are 6 rings and 10 cells. Now the total is 10 parasites and 17 WBC. But in the third field, there is no parasite, but there are 8 white blood cells. The total for parasites is 10 so far, but that of WBC has increased to 25. Then in field number 4, there are 3 parasites and 5 WBCs. The total of parasites is now 13. WBC is 30. Then in field 5, there is only 1 parasite and there is no white blood cell. So the total is 1. The total is now 14 parasites and that of WBC is 30. Then in field number 6, there are 6 parasites and 12 WBCs. Our total is 12 parasites and 42 white blood cells. If we are going to report this smear here by parasites per 200 WBCs, we continue counting these parasites and WBCs until when the number has reached 200 in the field where you see that you find the 200th WBC, count the parasites, all the parasites in that field and all the white blood cells. But if you are reporting per 200 WBC, you stop there and record that this number of parasites per 200 WBCs. Then there is a situation where you reach 200 WBCs, but the parasites are less than 10. If you reach 200 WBCs and the parasites are less than 10, it is advisable that you continue counting until when the WBC total count has reached 500. Then you report the number of parasites seen per 500 WBCs. Then, if our report is to be by parasite density is the number of parasites in a microliter of blood. What we do is, if we don't know the WBC count of that sample, we assume that the average WBC count is 8,000 per microliter, because the range is between 3 and 12. So if we know that true WBC density, it is what we use. But as we said earlier, we are counting both the parasites and the WBC simultaneously. Then we count up to 200. We count all in the field where we have found our 200th white blood cell. If they are few, we continue up to 500. Now we count. If we calculate, not count. Now we calculate. We said we assume that the WBC total count, the average WBC total count is 8,000 in an adult person even in children, that we put that as the absolute count. Say you have done a CBC, we put the absolute count on as a numerator on the left side. Then the denominator here is the WBCs we have counted. Say they are 200, 205, 500, like that. Then the parasites counted at the new is we put it as the numerator on the right side. The parasites we want per microliter is these are the parasites we want per microliter is the numerator on the right side, and the parasites we have counted as the denominator. We have said the WBC count is the numerator on the left side, and the WBCs we have counted is the denominator on the left side. The parasites per microliter, the parasite density we want is the numerator here, and the parasites count is here. Or our parasite density is equal to WBC count times parasites counted divided by the WBCs counted. For example, if you have counted 87 parasites in 204 WBCs, it will be 8,000, the average absolute WBC count, times 87, the number of parasites, divided by 204. Then our parasite density will be 3,412 parasites per microliter. Then, if our density is very high, the parastemia is so high, we are advised to use a thin film to calculate parasite density. When you are using a thin film to calculate parasite density, you count the proportion of infected red blood cells, because in a thin film, the cells are not hemolyzed. How many infected red blood cells are there in a total of 5,000 red blood cells? What you get, you multiply it by 5 million, because this 5 million is the average WBC count per microliter. The parasite density in a thin film is the number of infected red blood cells divided by 5,000. Those, because we count the infected red blood cells in a total of 5,000 red blood cells in a smear, then we multiply it by 5 million, the average count of the average red blood cell count. Also, this 5,000, you use it if you don't know the specific WBC count of that specimen. Then that has been parasites per 200, where we say we count the number of parasites against white blood cells up to the 200th white blood cell. Then we report number of parasites per 200 WBC. If the parasites will reach 200 cells and the parasites are less than 10, we continue up to 500 WBCs. Then we report the parasites counted per 500 WBC. Then we can also report parasite density, that is parasites per microliter, where we report the number of parasites counted, multiply it by the absolute WBC count of the specimen, or by 8,000, then we divide by the number of white blood cells we have counted. That will be the parasite per microliter. If the parasite parastemia is too much to be counted in a thick film, we determine parasite density from a thin film, where we count the number of infected red blood cells in a total of 5,000 red blood cells. Then we multiply that by 5 million. Then after that, I take you to the plus method of reporting. Before we report using the plus method, we are advised to check at least 5 fields, because if I can take you back to this representation of ours, in the first 2 fields here, there were white blood cells and the parasites. But again, in field number 3, there are no parasite. In field number 5, there is a parasite, but there are no white blood cells. So if you are examining if you are going to report by the plus method, you need to examine at least 5 fields. You can even go up to 10 to see how the parasites are distributed. When you are going to use the plus method, count the parasites in a number of fields. If they are few, you can go up to 100 fields and then determine the average number of parasites per field. If the average number of parasites per field is 1 or less, we report that as a plus. If the average number of parasites per field is 1 or less, we report that as a +1. If the average number of parasites per field is between 2 and 19, report that as a +2. And if the average number of parasites per field is a +3, we report is 20, we report that as a +3. But WHO it doesn't recommend the plus system, but we use it since it is what is understood by most of our clinicians, but it's not a WHO recommended method. So we need to hold CMEs with our clinicians. If we are doing clinical work, then take them through the parasite density method. Also, there is another method called parasites per field. Parasites per field, what we do is we count the malaria parasites in the fields, only parasites. Then the total we count, we establish the average. We divide the total number of malaria parasites divided by the number of fields, then we report the parasites.
Kaga, are you there or it's my net?